At 200 degrees centigrade, how long would it take for the silicone rubber in figure 10.7 to relax 50%? Table 10.1 gives the chemical stress relaxation times for silicone rubber at different temperatures. So these relaxation times are estimated from the time necessary for sigma t over sigma 0 to drop to 1 over E, which is 0.368. So we have tau equals constant times e to the power delta E over RT, where delta E is the energy of activation. Taking ln on both sides, we can say ln tau equals ln of the constant plus delta E over R times 1 over T. So if we plot a graph of ln tau versus 1 over T, the slope will be delta E over R. Okay. So let's try to do that with the values that we have. We have tau, ln tau, temperature in centigrade, temperature in Kelvin, and 1 over T. The first value of tau is 48. So since tau is given as tau times 10 to the negative 4 seconds, tau will be 48 times 10 to the power 4. So ln tau would be 13.08. This is at temperature 250 centigrade, which is 523 Kelvin, and 1 over 523 is 0.0019. The next value of tau is 10.5, so it would be 10.5 times 10 to the 4 seconds. Ln tau would be 11.56, temperature 277, so temperature in Kelvin would be 550, and 1 over temperature would be 0.0018. The next value of tau is 2.145 times 10 to the power 4. Ln tau is 10.11. Temperature in centigrade is 301. In Kelvin is 574. So 1 over tau is 0.0017. Now we are ready to plot the graph. Ln tau goes from 10.11 to 13.08. So let's start with 10, 11, 12, 13, 14. And 1 over T goes from 0.0017 to 0.0019. So let's start, keep 0.0011. So this 0.0013, 0.0015, and 0.0017. The first point is 13.08 for ln tau and 0.0019 for 1 over T. The second is 11.56 for ln tau and 0.0018 for 1 over T. So that would be somewhere here. The third point is 0.0017 for 1 over T and 10.11 for ln tau. So that would be here. So the graph is something like this. This is a straight line. So I'm going to take the 2 points that are given, which is 0.08 minus 10.11 and 0.0019 minus 0.0017. So my slope is 14,850. So since the slope is 14,850, E act over R would be 14,850. If If we take R as 1.98 calories per mole per Kelvin, then delta E act equals 14,850 times 1.98, which is 29,403 calories, approximately equal to 29 kilocalories. The textbook gives a value of 35 kilocalories, which is approximately the same. So ln tau equals delta E activation over R times 1 over T. So we can say ln tau 1 over tau 2 equals delta E activation over R times 1 over T1 minus 1 over T2. Plugging in the values, ln 4.8 times 10 to the power 4 over tau 2 equals 14,850 times 1 over 523 Kelvin minus 1 over 473 Kelvin, which is 200 degrees centigrade. Sigma T over sigma 0 at 0.368 corresponds to a relaxation time of 935.6 times 10 to the power 4. So we want to find out, and this is at 200 degrees centigrade. So we want to find out the relaxation time at 50%. So that's a question. So at 0.5, what would tau be? Okay. So from the graph, if you look at the graph of the figure 10.7, you can see that sigma t over sigma 0 at time t is equal to 0 is 1.0, because at time t is equal to 0, there is no, it's not started yet, so sigma t is equal to sigma 0. Y is equal to mx plus b. So let's try to write the equation for the straight line at 200 degrees centigrade. We can take 2 points. One is 935.6 times 10 to the power 4 for the x coordinate, when 0.368 is the y coordinate, and another point, and then another point P2, which has the x coordinate as 0 and the y coordinate as 1.0, because sigma t over sigma 0 is equal to 1 at time t is equal to 0. So with these two coordinates, we can find the slope by taking the ratio of the difference of y coordinates over the difference of x coordinates. So the question being, how long would it take for the silicone rubber to relax to 50%? It would take 735.3 times 10 to the power 4 seconds to relax 50% at 200 degrees centigrade.